Hi everyone, my name is Kshitiz Khanal. I am a PhD student at the Department of City and Regional Planning at the University of North Carolina at Chapel Hill. Today I'm talking about assessing generalization performance of style transfer method to segment PV panels from aerial images. Deep learning-based computer vision models do not generalize well across images that are different from training images, and there's also a scarcity of training images in some geographies, especially in developing countries. So we would need models that generalize better across geographies if we were to use deep learning computer vision models for energy infrastructure applications. And the mechanisms governing generalization are still not well understood. It's an active area of research, but it's been empirically understood that having some amount of randomization in model through generative samples, generative architecture will contribute to generalization. And recently, a class of models called the conditional generative adversarial networks, they have shown some promise in having better generalization across out of sample images in different domains. So we are trying to assess the performance of a cGAN model called Pix for energy infrastructure applications. Um, and Pixel uses something called the style transfer, where we are trying to transfer the style from a sketch to a rendering of a bag, from a satellite image to a map rendering like Google Maps, and from day image to night image. And in our case, we're trying to transfer the style of an aerial image to a binary segmentation maps. And we're using a model called Pix developed by Isolatal Image. It's a GAN-based model. The generator is based on unit, and the discriminator is called PathScan. So our setups look like this. We have different images from different terrains, rock, saline, alkali, and rooftop. We use 1,000 images for each set of 50 test images, and then 200 epoch of training for each. So the results that we got were that for pix to pix and unit, it looked like when comparing training the models with roof images and testing with roof images, pix to pix seemed a bit undertrained. To put it in numbers, using the dice coefficient, we found the dice coefficient of pix to pix with 0.72 and unit with 0.91. So we realized that pix to pix would be a bit hard to train, and it turns out to be a really um, really popular problem. It's been found in different instances where training GANs is really hard. Uh, and the other thing that we did was we tried to compare the performance of model on images that look radically different than we used in training images. So when we use image of a desert with very little solar panel, both models do not perform that well. When we use image similar to training image, both models do well. But when we use an image that's somewhat different but not too different, like in this case, uh, yeah, an image of a roof that's not drone image, and that's from a random Google search. Pix2Pix did well for this one, better than unit. uh, so what we can say from these observations is that cGAN models may have some promise, but it's still inconclusive. We need to run more tests and design the test set a bit differently. And there's also a problem with increasing the training performance, because GANs are notoriously hard to train. So yeah, from the research, I can conclude that there may be some promise with cGAN models and GAN architectures in general for style transfers, but we need to increase training performance and decide and do more on how to test it for images that are very different from training images. So that's why this is the future research work that I plan to do to continue research that I did for the fellowship. And these are two my main references. One is for the dataset, one is for the fixed model. And finally, I would like to thank Albert Stone Foundation and Duke University Energy Analytics Fellowship Program for giving me an opportunity to develop my skills as a researcher and machine learning practitioner in the energy domain. Thank you.